Let's go to experiment 3. In this experiment, we start with the single bulb again, and it's bright. And then we replace that with 2 bulbs in parallel, and we find they're both bright. Now indeed, we didn't need both of these circuit boards. I could just open this switch. We saw this last day, right? When I close that switch, it doesn't affect this bulb at all. And this bulb becomes just as bright as that bulb. Okay, so what we saw is the 2 bulbs in parallel were just as bright as a single bulb. More flow, more glow means that if that's 5, you call it amps, I call it quarts of blueberry juice per second. This has to be 5, and that has to be 5. What goes around comes around. So if this is 5, that's got to be 5. What have I got here? 10. It's got to be 10. And I can see that by looking at this junction right there. If I blow that up, I see that every second that goes by, I've got to deliver 5 quarts of blueberry juice this way and 5 quarts of blueberry juice that way. That means I got to bring in every second 10 quarts of blueberry juice. Now in this case, am I sharing like a book or sharing like a pie? Like a pie. Now I'm sharing like a pie. I'm actually dividing it. If I think of Fred and his friends coming, they see 2 paths that look the same. There's no reason to choose one over the other. Half of them go one way, half of them go the other way. But the number coming in has to be equal to the sum. Now, in this case, I have exactly twice the current through this battery that I have through there. Why? Ohm's law. If this has resistance R, 2 identical paths have half the resistance of a single path if they're parallel. Right? That's what we learned last day. So that means that this resistance is going to be half of that resistance. If I use V equals IR, if the resistance gets smaller by half, the current has to double. Check that your neighbor's on the bus. If not, slap them away.